This is a pendulum setup where I have a bob with the mass given as 0.4 kilograms, starting at an angle of 20 degrees. And the question is, first of all, neglecting any friction or air resistance, what would be the speed at the bottom and what is the tension in the string at the bottom? We assume all of the mass is located in the bob down here. And so we're going to do this from an energy point of view, mostly because if we try to do F equals ma, while our mass is constant, the tension has to adjust, because as we go from a point up here to a point down at the bottom, the direction of the tension in relation to the mass is changing. So we can't use constant acceleration equations, so we've really got to do it from energy. So I'm going to call this the initial and this the final, and I'm going to set up my diagrams here to say this is my initial situation, and I have no kinetic energy because it's starting from rest, and so everything is in potential energy, which would be gravitational potential energy, which we would find if I set this as my y equals 0, so therefore my ug equals 0, then I just need this height right here, h, to be my gravitational potential energy initially. And so that's equal to E initial is equal to U initial, which is equal to mg, that h that's drawn. The initial kinetic energy is 0. And then at the bottom, which is our final, all of this energy goes into now kinetic energy. This should be the same height as before. So I guess I should make that like that. Because we're at y equals 0, so we have potential energy is equal to 0. So if I set up my E final, that would just be U final is equal to 0, kinetic final is equal to 1/2 mv squared, and so I'm going to say E initial is equal to E final, or mgh plus 0 is equal to 0 plus 1/2 mv squared, and that gives me mgh is equal to 1/2 mv squared. The masses cancel, and I can bring the 2 over. 2gh is equal to v squared, or v is equal to the square root of 2gh. And in order to find the height, I'm going to use the angle, because I'm going to recognize that, oh, I also need the length of this, otherwise I can't do anything. And the length of this pendulum was 2 meters, according to the original problem. Sorry, length is 2 meters. So this height, if I find this side right here that I'm highlighting, this yellow highlighted side, which I can from trig, and I subtract it from the length, that will give me the height. So I'm going to say this side, if I just set up my trig, this is my adjacent, and that's my hypotenuse, so I can say cosine of theta is equal to this, we'll call this Ly, I guess. Ly, the y component, sort of, L, or that length, if you want. And so I can find that length there. If I subtract it from the overall length, that gives me the height. So my height, put it right here, my height is given by L minus L cosine theta, because I write this Ly as L cosine theta. So I can put this, I can calculate my height, so that would be L times 1 minus cosine theta, which for 2 meters, and 1 minus cosine of 20 meters gives me a height of about 0.12 meters. I substitute that into there, and I get my speed to be 1.53 meters per second. So that answers the speed at the bottom. V is 1.53 meters per second. To find the tension, I can find the tension at any point once I know the speed, because the tension, if we look at this bob at the bottom, I've got an mg that's down, I have tension that's straight up, but that tension has to be bigger because there is this, remember, acceleration towards the center. It's still going in a circle, right? It's swinging and it's starting to mark out a circle. It's a circle with a radius of 2 meters. And so from my force diagram, this gives me tension up minus mg is equal to ma. So now I've reverted to forces in the y direction equals mass times acceleration in the y, but this acceleration in this case is centripetal acceleration. And so in place of that, I'm going to put my v squared over my radius, which would be 2 meters. And my tension, that just equals, I add mg to both sides. I get m v squared over 2 meters. Sorry, this is not the same as the m for the mass. Plus mg. And so substituting everything in, I get tension is equal to, what was my mass? 0.4 kilograms times 1.53 meters per second squared over 2 meters plus 0.4 kilograms times 9.8 meters per second squared. This is 3.92 newtons, and this altogether I calculate to be 0.47 newtons. So you can see that the tension is slightly bigger than the weight because it's got to provide that centripetal acceleration. So I add those two and the tension is just 4.39 newtons at the bottom. The tension is going to adjust as it needs to keep this motion. Okay, that was all of part 1. Now part 2 says if our speed is equal to this at the bottom, which is less than our 1.53, what percentage of the initial energy got converted to thermal energy? Okay, so let's rewrite what we've got. So at the bottom, what actually happened was a speed of 1.4 meters per second, where we expected 1.3 without friction, but there's obviously some friction and air resistance, and actually a fair amount. And so what we want to do is say, what's our energy initial and what's our energy final with this speed? And so we can just use the same equations we had up here, which is mgh plus 0, and we're going to compare that to our 0 plus 1/2 mv squared. So this is our potential, no kinetic to start with, and no potential energy and just kinetic afterwards. And so when I calculate this out, putting in my values, this gives me 0.47 joules, and this one gives me 0.39 joules. And so we can see that it's less than when we started, so we lost some amount, and so we can say 0.39 joules is equal to what percentage? X percentage of 0.47 joules. You can work this any number of ways if you want. This X percentage is 83%, which means we lost 17% of the initial. Okay, and so that's how we deal with frictional situations. We say, hey, lost, we need to say 15% initial went into thermal energy. In this case, probably heating up the air, but it may be that the pivot also had some friction right up at the top. So that's a possibility as well.